Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to discuss Young's double slit experiment. Young's double slit experiment is a very basic experiment to demonstrate the wave nature of light. Let's take a look at a typical YDSE. Slits S1 and S2 symmetrical to source S, which act as two coherent sources in same phase and separated by distance d. Waves from S1 and S2 interfere at a point P on a screen at a large distance d, such that d is very less than d. For this case, waves from S1 and S2 which are reaching at P are parallel and make angle theta from the central reference line as shown in the figure. Also, if P is very near to the center of the screen, that is Y is very small, then theta will be so small that we can take sin theta is equal to tan theta is equal to theta. Now, geometrical path difference of waves at P, that will be also the optical path difference in this case, will be S2P minus S1P, that is S2M, that is equal to S1 S2 sin theta or d sin theta, which will be equal to d theta. For theta to be very small, for this theta is equal to sin theta is equal to tan theta is equal to y upon d. Therefore, path difference S2M, let denote it as delta x is equal to dy by d. Since there is no phase difference at source S1 and S2, therefore at P phase difference is only due to the path difference, that is delta phi is equal to 2 pi by lambda delta x, that is equal to 2 pi by lambda dy by d. Now for constructive interference, the phase difference 2 pi by lambda dy by d will be equal to 2n pi, where n is equal to 0, 1, 2, 3 and so on. For this, y will be equal to n lambda d by d, which gives position of maximas, and for n equal to 0, that is y equal to 0, we get center maxima, and for n equal to 1, 2, 3 and so on, we get first, second and third order of maximas respectively. And for destructive interference, phase difference 2 pi by lambda dy by d will be equal to 2n plus 1 pi. From this, we get positions of minima will be equal to n plus half lambda d by d. For n equal to 0, 1, 2, 3 and so on, we get first, second, third orders of minimas respectively. Due to geometrical symmetry, we get same patterns of maximas and minimas in both sides of central maxima on the screen. Therefore, we get positions of maximas at y max equal to 0 plus minus lambda d by d plus minus 2 lambda d by d, etc. And positions of minimas at y minimum is equal to plus minus half lambda d by d plus minus 3 by 2 lambda d by d, etc. With respect to the origin O, which is the central maxima, from the above we can see that there will be alternate maximas and minimas on the screen. We are going to discuss about fringe width and angular fringe width in a typical YDSE experiment. Between the two consecutive minimas, there is a dark fringe, and its width is the difference in positions of two consecutive minimas, that is equal to n plus 1 lambda d by d minus n lambda d by d is equal to lambda d by d. And between the two consecutive minimas, there is bright fringe having width n plus 1 plus half lambda d by d minus n plus half lambda d by d, that is equal to lambda d by d. Therefore, for a common YDSE, dark and bright fringes have same width, that is equal to lambda d by d, and this is for d very less than d or theta tending to 0. And angular fringe width theta naught will be equal to fringe width upon distance between the slit planes and the screen, that will be equal to lambda upon d. We are going to discuss the YDSE with a thin plane sheet. Introducing a thin transparent plane sheet of thickness t and refractive index mu in front of a slit, shift the fringe pattern on the screen. Let's take a look at the figure. For interference at P, optical path length from S1 will be equal to geometrical path length in vacuum plus mu times geometrical path length in the transparent medium of the sheet, that will be equal to S1P minus t plus mu t, that will be equal to S1P plus mu minus 1 into t. And optical path length from S2 will be same as geometrical path length S2P. Therefore, for 0 order maxima, S2P minus S1P plus mu minus 1 into t will be equal to 0, or S2P minus S1P is equal to mu minus 1 into t. And for d very less than d and theta tending to 0, S2P minus S1P is equal to d theta, that will be equal to mu minus 1 into t. So dy by d is equal to mu minus 1 into t, or y will be equal to mu minus 1 into t into d by d, which gives the new position of the previous central maxima. Therefore, entire fringe pattern will shift in the direction where transparent sheet is introduced. And for nth order maxima, phase difference at P, delta phi will be equal to 2n pi. Therefore, phase difference, that will be 2 pi by lambda into optical path difference will be 2 pi by lambda into d theta minus mu minus 1 into t. And so d theta will be equal to mu minus 1 into t plus n lambda. Since theta is yn upon d, therefore position of nth order maxima yn will be equal to d upon d into mu minus 1 into t plus n lambda, and position of n plus 1th order maxima yn plus 1 is equal to d upon d mu minus 1 into t plus n plus 1 lambda. And fringe width beta will be yn plus 1 minus yn, that will be equal to lambda d upon d, that will be lambda d upon d, which will remain unchanged. Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to discuss YDSE with different arrangement of thin plane sheets in path of the interfering waves. Let's take a look at the given YDSE arrangement. A sheet of refractive index μ1 having thickness T1 placed in front of slit S1 and a sheet of refractive index μ2 having thickness T2 placed behind the slit S2. For the wave 1 reaching at P, optical path length from the source S to P through S1 will be SS1 plus S1P plus μ1 minus 1 into T1, and for the wave 2 reaching at P, optical path length from source S to P through S2 will be SS2 plus S2P plus μ2 minus 1 into T2. Therefore, path difference for wave 1 and wave 2 reaching at P will be delta x, that is equal to SS2 minus SS1 plus S2P minus S1P plus μ2 minus 1 into T2 minus μ1 minus 1 into T1. Since SS1 is equal to SS2 and S2P minus S1P for d very less than d and theta tending to 0 will be d theta. Therefore, optical path difference delta x will be equal to d theta plus μ2 minus 1 into T2 minus μ1 minus 1 into T1. And for delta x equal to 0, theta gives the angular position of knee position of previous central maxima, and for delta x equal to n lambda, theta gives the position of nth order maxima. We are going to discuss YDSE using white light. At center of the screen, path difference of the two waves from S1 and S2, delta x will be 0 for all wavelengths. So, center of the screen is white due to overlap of maximas of all wavelengths. For the points where path difference delta x is n plus half lambda r d by d, there will be minima for red. So, red is absent and violet dominates in the fringe color. And for delta x is n plus half lambda v d by d, there will be minima for violet. So, violet is absent and reddish colored fringe is appeared. Maximas of two wavelengths lambda 1 and lambda 2 overlap if any set of values of integer n1 and n2 satisfies the relation n1 lambda 1 d by d is equal to n2 lambda 2 d by d. To discuss a typical YDSE having slits of different sizes. Wave 1 and wave 2 from the slits S1 and S2 have different amplitude A1 and A2. At P, wave 1 and wave 2 will be given as y1 is equal to A1 sin omega t and y2 is equal to A2 sin omega t plus delta phi, where delta phi is the phase difference between the two interfering waves at P, which is equal to 2 pi by lambda into path length difference delta x, which will be d theta for d very less than d and theta tending to 0, or y very small, that is for P very near to the center of the screen. Therefore, amplitude of the resultant wave at P will be root of A1 square plus A2 square plus 2A1 A2 cos delta phi, and maximum amplitude A maximum will be A1 plus A2 and minimum amplitude will be A1 difference A2, which will not be 0 if A1 does not equal to A2. Therefore, in this case, no complete dark fringe is observed. Welcome to Not for Exam, and I am your host Sujit, and we are going to discuss YDSE for d very less than d but very large theta, that is the angular position of the interference on the screen. Let's take a look at the given figure. For d very less than d, wave 1 and wave 2 will be parallel, but since theta is very large, sin theta cannot be equal to tan theta, cannot be equal to theta. Therefore, two waves reaching at angular position theta at point P on the screen have path length difference delta x will be d sin theta, and for positions of maximas d sin theta will be n lambda, and for positions of minimas d sin theta will be equal to n plus half lambda, where n is equal to 0, 1, 2, 3 and so on. Since maximum value of theta is 90 degree or sin theta is 1, therefore maximum order of bright fringe will be greatest integer of d upon lambda. Therefore, total number of bright fringes including center bright fringe and including maxima at infinity will be equal to twice of greatest integer of d upon lambda plus 1, and total number of minimas will be twice of greatest integer of d upon lambda plus half including minima at infinity. And we are going to discuss YDSE when d is comparable to d. Let's take a look at the given figure. Path difference delta x S2p minus S1p by geometry will be equal to root of y plus d by 2 whole square plus d square minus root of y minus d by 2 whole square plus d square, and delta x will be n lambda for constructive interference and delta x will be n plus half lambda for destructive interference. Also, maximum order of bright fringe will be equal to greatest integer of d upon lambda, and total bright fringes will be equal to twice of greatest integer of d upon lambda plus 1 including central maxima and maxima at infinity, and total number of dark fringes will be twice of greatest integer of d upon lambda plus half